Hi, and welcome to this Hopper internals video. Hopper is a modern semicolon and curly brace language similar to Java and C Sharp, but designed to run on small devices like microcontrollers or like 8-bit microprocessors like the 6502 or the Z80. On the channel, there's a lot of videos, but they're broken into playlists. So if you're new to this, I suggest you go and go look at the Hopper language playlist. Or look at some of the tutorial videos to get how to get started with the Hopper development environment, which includes an editor, debugger, all that, and how to get it up and running on your Windows machine. Anyway, enough of an intro. Let's move on to the video. So, what I'm talking about today is something I'm coming up with called the Hopper minimal runtime. So, by default, the Hopper runtime has been running on Windows for a while, and it's been running on the RP2040 microcontroller. And last year I wrote a runtime for the 6502. I hand coded that. Let's do that. So I'll just demo it quickly. Let's get this up and running on the device. So I compiled this, successful compiling, and I'll use the Hopper monitor, which is it's a debugging interface for connecting directly. I'm connected directly to this 6502 machine that's running on this RetroShield by 8-bit Force. And let's load up that Fibonacci program that I just compiled. It's on the device, and I can now source level have a look at what that compiled to. So what we're looking at is the Hopper bytecodes that run on the Hopper virtual machine, which is what I call the runtime, which is sitting on the 6502 machine. And you can see on the left here in this column that each of these instructions, enter, push immediate, push delegate, pop local, push immediate, they're each 3 bytes wide with the exception of the system call one. So this is what happens if you don't use packed instructions. It uses all the default instructions, and it's a lot less instructions, but the code isn't very dense, so your programs end up being pretty big. So size of our program is 1E8, so that's it in hex, the hex size of our program. So yeah, about 500 bytes roughly, more than half a K, just to do the Fibonacci sequence program. Anyway, if we step through it, enter sets up a stack frame, so I'll step through that. Now we're on push I, push immediate 0, so that'll push 0 onto the stack. It's a 16-bit stack slot, no matter which platform you're running on, so that's pushed 16 bits worth of 0 onto the stack. Now we're going to push 1 onto the stack, which is the index of the delegate. It's actually a function index, so these have to always stay 16-bit because they get replaced with 16-bit addresses at runtime. And what are we on now? Pop local. So it's pushed 0 to make a slot on the stack, pushed a 1 above it. Let's have a look at the value stack. There's the 0 that it pushed onto the bottom of the stack, then it pushed this 1, and now pop local to 0. So it's going to pop whatever's on the top of the stack to stack address 0. So that 1 should go into the bottom slot and the top slot should go away. So let's step over that and look at the stack again. There we go. So the 1's back in the bottom of the stack. All right, now we're on like another push. Let's just push another 0. And now we're going to push a 4. Right, I think that's enough to illustrate my point. So there's our stack with our 1, a 0, and a 4. Right, so now let's go back to the editor. We edit Fibo, Fibonacci. And inside here, we're going to say, no, we're happy with, we want packed instructions. Right, and let's go back and load it back up to the 6502. Load Fibo. There we go. It's a lot smaller. So it was 1E8, which was 488 bytes. So now it is 125, which is that's hex. Let's do that again. I've got a little calculator on the side, 125. Now it's 293. So it's almost half the size. Okay, let's have a look at the source. So very notable here, if you recall, these were 3 bytes wide on almost all of them except for the syscall last time. Now the syscall is actually 3 because it's been combined with another instruction. The enter is no longer enter, it's enter B with the 1. So when I step over enter, when I execute enter and now I look at the stack, it actually created a stack slot. That's what the 1 was. It created me 1 empty stack slot. Because at the beginning of your function, you're often creating local variables. And each of them is really just a stack slot. So you could have enter 5 and you would have 5 slots created in a single instruction. Again, we're going to push our 1, and like I said, it has to stay 16 bits because that space gets substituted by an actual runtime address at some point. So we'll push the 1, and we should have 2 things on the stack again. We step again with the pop local, and now the pop local is only 1 byte instruction because it's actually pop local 0. So because that happens a lot too. Push and pop of 0 and 1, often you'll have local variables that get used a lot in small functions. So over time, I figured out which of these I should make into short instructions to get the code density to be quite high. So let's pop that. So we should have 1 on the stack again, just 1. And then we had those 2 more instructions that pushed a 0. And then there was another instruction that pushed a 4. It's being combined now with the system call, because the system call was only 3 bytes wide. 2 bytes wide. There was an extra spare byte. So often before you call a system call, you might push an integer onto the stack, and often that integer is a small integer, so it'll fit inside a byte. So syscall B0 pushes that 4 onto the stack and then does the system call. So we won't even see it happen. So if we go back now, we got our new string fiber on the stack, and 4 was really the length of the string it was going to create. Yeah. Anyway, you get the idea. Packed instructions, smaller. And small is a good thing because it means that you can run a bigger Hopper program on your small device if the code is smaller. So if the code is half the size, you can write twice as big a program. The other thing that's good about smaller is it executes faster. So on these devices, if I have to fetch less bytes for the operands and fetch less bytes because there's less instructions, these 2 instructions are combined into 1, or that very first instruction. Let's go back there. So I can go to restart here. This enter B here is now 1 instruction. It's a wider instruction, but it merged that first push 0 into it. So you get faster execution because you've got less instructions to execute or less operands to go and fetch, and you get higher density code. So that's what the packed instructions are about. It's basically about packing more instruction bang into less bytes, right? And in case you thought this was how you develop in Hopper on your 6502, I was just using it to show you the bytecode. That's my debugger for debugging the runtime. If I was debugging Hopper, I'd use this debugger. I just pressed F5 in the editor, and the title bar changes to green. I'm now in the source level debugger. So now I can step through here with all the usual sort of Visual Studio keys and step into my debugger. And on the right, let's show you that. Let's get rid of the video. On the right here, you can see your stack, your call stack, along with the arguments, local variables. So if we go and this is a function delegate. That was the delegate. So it's calling a function delegate to call this Fibonacci main function here. We go in, and it's going to call itself a few times. And you can see the stack growing here. And then we could say put a breakpoint here, press F5 to run. And then once it's finished, yeah, we're at the breakpoint now. So it stopped at the breakpoint. The result is 55, which is what we expected because Fibonacci 10 is 55. And then we can carry on stepping there. And I can step into these. So if I step into this Reitlin with the toString, in the minimal runtime, the 2 ways that I made it minimal was the one was to not implement all the instructions. So don't implement the packed instructions. They really are optional. They're an optimization to make the code faster and smaller. So you can live without them and have a full Hopper in runtime. It'd just be bigger programs and slower. The other way to make the runtime smaller was to not implement all the system APIs in the runtime. So if I step into Reitlin, well, that's in the append, where the plus adding the two strings together. And now it's in the toString. And all of this is written in Hopper, and I'm stepping through it in the debugger. So my toString has to go around twice because there's 2 digits in the number 10, and there we go. We're back out. Then we have to append that one and append another one, and you know, this could take a while. So let's go back to where it was. I can double click on the stack. So that whole string, concatenating all that functionality together here, takes a while. But it's stepping through a lot of Hopper code. These are not system APIs. So let's go and have a look at that. So normally, when you write a Hopper program, you would use source system like that. And that's the full Hopper environment. And you can see there's things like dictionaries and lists, there's files and directories. But if we go in here and look at the character unit, so it has units and programs like Pascal does. If you go and look at the character unit, you'll notice that in the full Hopper, these little functions are all system functions. And the reason is because the Hopper compiler is written in Hopper, and it uses the scanner and tokenizer use these functions a lot. So Hopper is much, much faster if these are system functions. Whereas, and the navigation here is like all shortcut keys. I'm control backspace to go back where I was the previous time, right click on there to go into there, right click on there. So this is the minimal system. So it's a different folder. You can look on the right here. So instead of saying system, it's minimal system. And if I go in there, it's into character, it's minimal character rather than system character. And you'll see here that there are no system functions. There's no little system behind any of them. They're all written in Hopper. So the disadvantage of this is it makes them slower. The advantage is I didn't have to write them in 6502 assembler. They're all written in Hopper. Let's go look at the string one. So the string, the full system string had like 20 system functions. The minimal one only has a half a dozen, and everything else, as we saw with the append we were stepping through, and the toString and all that, everything else is written in Hopper. So it relies on the minimal subset of built-in system functions, and then all the other system functions are written in Hopper rather than being built in. So like I said, this advantage is it's slow. I can right click on a type and go to the unit as well. So I went to uint. Good example here. If you were ever parsing a string into a uint, like, you know, you've got a number in a string and you want to parse it, which could also be hex and it could also be binary, which means if I right click on this, I'll go and have a look at that one. You could parse binary. There's a lot of code here. So A, this would be a lot of code to write in 6502 code to make this a system function. And B, it would make the runtime bigger. You know, it would make the Hopper runtime on the 6502 bigger. So the disadvantage, like I said, is it's going to be slower because this is being interpreted on the virtual machine rather than running as native code. But there's a ironic advantage, and that is if you don't parse strings anywhere in your program into numbers, if you don't use this functionality, then the optimizer will just remove it. So, and it won't exist in your program, which means your program will be smaller. So even though all of these are written in Hopper, well, in Hopper they're smaller anyway because the code density of Hopper of the Hopper bytecodes is way higher than, say, machine code instructions on 6502. So that's an advantage of writing the runtime library in Hopper is A, it only includes the bits you use, so it's not baked into the runtime, and B, it's smaller. So let's go and have a look at the 6502 part now, and then we can wrap this up. So what does it look like? I built a new toolchain for 6502, so I've got an assembler and an optimizer for 6502 assembler. So this looks strikingly similar to Hopper code, but it's not. You know, like it's got user statements, it's got units, etc. But inside it all, it's all 6502 assembly code. And then it's got some tricks that I've added to it. So since you're in a very much a semicolon curly brace kind of environment, you might as well have if statements, you know, on a flag on the CPU. And there's switch statements and there's loops and all that sort of stuff that you'd expect. And you can right click on things to go to their definitions like that, and control backspace to go back. These are constants. You can right click to go to them for the zero page use of the zero page here. It's my zero page allocation. Expressions are in regular parentheses, like these here. So it's an expression in a sort of a C syntax rather than an assembler syntax, because if you're switching between these languages all day, between say Hopper and this assembler, it's kind of nice if they're the same syntax. So it uses hex. This assembler syntax uses hex like C rather than with a $, which normal assemblers do. The comments are double slash rather than a semicolon. Anyway, and then yeah, a reference, an address that uses a reference uses the square brackets rather than the round parentheses, because that's what C does. You know, if you access an array element in C, or you use square brackets. So it's very comfortable to switch between this form of assembler and Hopper all the time. So here's the crux of it all. My arbitrary goal, it's not that arbitrary though, was to try and get the minimal Hopper runtime on the 6502 and the Z80 to fit within to 8K, because 8K ROMs are common, and then that means you've got all the rest of the space available for RAM. So you know, typically it's going to end up being 16K, and you're going to end up with 48K RAM. But in theory, you could have 56K of RAM and 8K of ROM. And then this is about as far as I've got right now in terms of what fits in 8K. If I actually keep all the packed instructions and I keep my fast integer stuff, and I'm running on the newer version, you know, 4 years younger with more instructions, then I can get quite a lot more into an 8K ROM. If I'm running on the original MOS 6502, which is what this one here is, then I have to give up the fast ints to get it into, and the packed instructions to get it into the 8K slot. So let's go and have a look at just how small the runtime library is. So function indexes in the runtime library are 1 byte, so there can be a maximum of 256 runtime library functions. And I haven't used them all after about 2 years. I'm kind of being, there's another whole set called libraries, which are always written in Hopper on the microcontrollers. And so I've been quite careful as to how I allocate them. But in the minimal runtime, I re-indexed them so they all started, you know, they start at 0 and they run contiguously, because it makes the switch statement faster when you're executing. And there are only 26. So of the almost, you know, over 200 runtime functions in the full Hopper runtime, the minimal runtime can get away with only using 26 system functions. And you saw the string ones. There were about 6 of them. There's some array ones. I've got 2 time ones, and because these are common things you're going to want to do, is to time things and do a delay. Then there's the serial port, which is connected, and then some that you don't get on the Windows one are these memory allocate ones, which are kind of handy. And that's about it in terms of that's it. That's the runtime. So let's go back and look at the instructions. There's more instructions. There's a few dozen of the instructions that are the minimum set that you need to run a full Hopper runtime. A couple of dozen of them, and this is them. And then the packed instructions, which I've also implemented. So yeah, you can build this, and then it'll be 16, you know, well, it's not 16K, it's about 12K with all the packed instructions as well, not just the packed instructions. But these are the extra packed instructions that I implemented as well. And then in addition to that, the other thing I did, which is optional, is fast integers. So fast multipliers and fast divides. So you can easily if-def this out and you get like another 500 bytes back. But there's a lot of, I mean, the obvious things you can do is like dividing by 1 is an obvious optimization, or multiplying by 0, or multiplying by 1, obvious optimizations. Multiplying and dividing by 2, you do shifts instead, etc. So they're obvious optimizations to do, but they take up space. So there's something you can sacrifice if you're trying to squeeze it into smaller space. Anyway, what I'd like to do with this is, on my Discord server for Hopper, I've got a channel for 6502. And I think it'd be great to have snippets of code in there and have people give input into how we can make it smaller. So problem areas, just look at bits of code that look too big and say, how would you make that smaller? It's like when I look at stack functionality and these are all the pushes and pops that are happening. And there's optimizations depending on which version of the 6502 you're using. And yeah, the if-def syntax very similar to C. But it would be great to have a dialogue to look at little snippets of code like this and saying, you're doing it wrong. Why don't you do it this way? There's a way to make this smaller. You can shave off a few bytes here and there. And if you shave off a few bytes here and there, they add up. Yeah. Anyhow, thanks for watching. If you're interested in participating, especially in trying to optimize little bits of code, you can just look at them and say, hey, I think you could do this differently. Just message me and I'll send you an invite to the Discord server. And I'll do another video on this 6502 toolchain, just on all the features of this assembler. Because it's got things in assembler that you wouldn't normally have, like namespaces, public, private. You can have let's have a look at how I did memory. Right clicked on there to go there. So I've got separate units for allocate and free because they're quite big in terms of functions. So when I go and look at allocate and free, so this unit's called memory. So it's a friend of memory. So that means the private methods in here, like allocate, which is lowercase. So just like Google's Go language, lowercase means private. If lowercase first character of an identifier means private, and uppercase means public. But friend can see the lowercase ones. Same with the garbage collector. And then, I can right click on things to travel to them. It's not letting me right click on those, but back to there. So the garbage collector is just like, these are the types that are currently supported. So I haven't supported all the reference types in this minimal runtime. There's no dictionary and there's no list type. But having strings and arrays is pretty cool. It's pretty functional languages. I've got some pretty cool demos running in it just with dictionaries and, just with arrays and strings. Yep. All right. Like I said, thank you for watching, and let me know if you want to invite to the Discord service so that you can participate in trying to help me optimize.